Hey,
Doing, Liam?
how you going?
Good.
So let me get this.
Yeah, go for it.
I don't want to screen on the application window. That one. Okay. And then when I do the view,
That looks good.
yeah, view. There we go.
Perfect. Yeah, that'll be great.
Okay.
All right.
All right. Whoop, why did it change? Go back.
No worries.
It's doing an automatic one. Why is it doing that? Hang on, I did the wrong thing.
No worries.
Weird. Hit stop. There you go. All right.
Looks good. Looks good. All right. I'll just we're going to hang out for just a little bit. This session officially starts at 2:30 in just a couple of minutes.
Yeah.
And while we're waiting, feel free to introduce yourself in the chat and say why you're interested in this presentation. And we'll start in a little bit. How's the weather over in North Carolina?
Stormy.
Stormy, huh?
Yeah, but it's just about cleared, just about gone past. But we had like really strong winds came through middle of the day.
Is that related to any kind of that? I know there was a hurricane down south, but I don't know
Yeah,
if
I
that
think it was that Louisiana
Mhm.
weather pattern, hurricane, whatever it was, whatever came ashore in Louisiana.
Yeah. Sometimes that can affect things far and wide.
Yeah. So.
All right, if you're just joining us, we're going to start in a little bit, probably a couple minutes. While we're waiting, feel free to say hi in the chat. Let us know why you're interested in today's presentation. I think it's going to be a good one. All right, so we've got about 17 people in the room so far, and we're right at the start time. Do you feel comfortable starting now, Liam, or would you like to wait for just a moment?
Whenever you want to start, I'm ready.
Okay, let's go ahead and get started then. Oh, I will say really fast, Jerry is a DevOps engineer who's been working with Salt for a while and wants to expand into event flow and orchestration. So sounds pretty good. All right, let's go ahead and get started. So welcome to this session about Salt's evolution from configuration management to orchestration and beyond. With Liam. Liam Greenwood is from the University of North Carolina at Chapel Hill, and he's going to give a more detailed introduction of his role and things like that. Before I get started, just have a couple of quick announcements. During the presentation, you can double click on the slides when you see them to make sure that they're at a nice viewing size. That'll make them a little bit larger. And Liam has said that you are welcome to ask questions in the chat, and then he'll answer them at the end of each slide. So he'll take them little bit by little bit during the session. And without further ado, I'm going to turn it over to you, Liam. Thanks.
All right. Thank you very much. And thank you all for spending some time here. Appreciate it. So, like I said, I'm Liam Greenwood. I'm the IT manager for Advanced Computing Infrastructure for a group called ITS Research Computing at the University of North Carolina at Chapel Hill, which is an awful mouthful. My email's there. My position's a new one. It was created in 2017, and it's very operationally focused. I have a small team. It's 7 Linux and Windows admin, and they're the one that makes stuff happening. I'm the manager. I'm the one that orchestrates what we do. I'm not the type on the keyboard everyday person. One of the things I was tasked with was productionizing our infrastructure without breaking value to the user constituency. So that's where I've been at. Research computing at UNC is central, institutionally scoped, world-class computing infrastructure. And we provide that, and we provide other technology tools and capabilities to support the research need of anyone who's affiliated with UNC at Chapel Hill. So the win with this is that anyone who wants to start their research and needs compute resource doesn't have to find funding to do so. So our goal is to provide state-of-the-art environment that will support high-level multidisciplinary research, and of course, help us become the premier research university in the United States, because that's what we all want to be, right? So there's a bit of a challenge there in that because we are institutionally scoped, and because anyone at UNC can utilize our facilities, we can't specialize particularly. We can't optimize for a particular workflow. We can't. We don't have workloads that we can predict. So it's a little bit of a challenge in that respect. The plus side is we're centrally funded, and so we're available to anyone regardless of whether they have grants or not. So that's pretty exciting. And a couple of years ago, someone at UNC got a Nobel Prize, and they ran some of their code on the computers we run, and that's really exciting to us as well. Research computing is made up of 2 groups. One's called engagement, one's called operation. Engagement is the outreach to researchers to talk to them about how to run their code and things. And operations, which this split out happened, like I say, in 2017, we run the infrastructure. That's our primary focus. So what do? We run a couple of clusters, and I'll talk a little bit more about our clusters because that's where we primarily use SALT. We have a thing called Secure Research Workstations, which is mostly Windows managed through AD, although there are secure FTP servers attached to those, and those are managed with SALT. We have VCL, which is another virtual environment. We're the organization that runs the infrastructure for iBiblio. iBiblio runs things like the Gutenberg Project, Grok Law, stuff like that. And they're a little interesting for us because we inherited them about 2 years ago, and they're not SALT. They're Puppet and Ansible. So we have a small footprint of that. We do about 30 petabytes of storage for researchers. We do VMware hosting. We do computational GPUs, and so on. And we do fun things like we manage a image render farm for Moorhead Planetarium where they do their shows. And we have a lot of fun. It's very exciting to be working with researchers and providing infrastructure for researchers. A little different than enterprise-style applications. What we don't do? We don't do anything with researchers' data. We don't run their pipelines for them. We don't do backups, and we don't provide disaster recovery. So, again, we're a little odd in the world because mostly backups and disaster recovery are things you always have to think of, and I don't. So it's kind of an interesting world. One of the biggest differences in what we do is that we provide access to compute resources via direct login, which is unusual. Mostly these days, people provide applications hosted in a web environment. We provide shell accounts. We have over 600 users with shell accounts. Those users are allowed to run ad hoc code from accounts on those nodes. They can compile whatever they want and run it. So it's a little different environment. You don't normally have, as a infrastructure runner, you don't normally have direct login of users. They're usually separated by the separate out into the application. But again, the 600 users are all managed with magical scripts and such like. So, it's a doable thing. So where do we use Salt? So initially that was primarily on our compute clusters, but we've got to the point now, a few years down the road, where we manage all of our Linux systems. I'd say most, because there's a couple that we haven't managed to saltify, but we manage with Salt our Linux systems, even if it's a unicorn, even if it's a unique system that has nothing in common with anyone else, we still do that. And it's a thing we do for researchers. Researchers don't all do cluster work. Sometimes they want to run a web app. Sometimes they want a database or something. We will stand those up on our infrastructure, but we will manage them through Salt like we do with our clusters. We currently don't use Salt on Windows. They're all AD managed. But we are looking at Salt to potentially help us with installation of packages on our VDI environment. But that's it's a pretty big step for us to do, and we haven't moved on that yet. That's a big change. So our clusters, we have two of them. We have one that's now about 3 years old. It's for massively parallel workloads. It's got 253 nodes, 15,000 cores, 100 plus terabytes of memory. This is all connected with low latency InfiniBand connections. And the challenge here is that they all have to be very identical, because when you go and run your massively parallel workload, you're absolutely dependent on every compute node that your job runs on being identical to the other compute nodes you're running on. And it's a reasonable size number of nodes that we have to look after there. That's in some ways the simpler of our two. The other one is Longleaf, which is kind of interesting. Traditionally, compute clusters have been very homogeneous. Everything in it much the same, and you update it on a time basis or when you have money. Longleaf was put together about 6 years ago, and its aim is to provide a platform for jobs that do not span hosts, does high throughput, data-driven workloads, does not do MPI workloads. So we split at that level. Currently, we've got about 310 nodes on there, and they're not all the same. They're all similar, but they're not the same. So we have a number of 280 nearly nodes varying from 24 to 36 cores, different amounts of memory. We have some large memory compute nodes. We have some big data nodes. We have GPU nodes, and so on. Our total's about just under 9,000 cores, 18,000 threads. And both of those are all managed through Salt, which is really the only way we can manage them, is with some automation tool like that. And Salt's worked well for us. And one of the challenges when you're looking at a cluster is, I can tell you a cluster is 200 or 300 systems. I can tell you it's 5,000 systems, but they're really like a really big appliance. You have to, when you roll your updates through, they have to be the same. All your all your installed software has to match, all your libraries have to match. The fact that your end users build code on there means that you have some other dependencies. The way a large compute cluster works is people submit their jobs to the environment, and the environment determines which particular compute node they run on. So therefore, we have to make sure that all the dependencies that an end user may have are available. Those dependencies are available on every single one of our compute nodes. We also have some other interesting things, like some research requires that software doesn't change. But the trick is mostly that every node needs to be the same. And one of the things you learn real early when you're doing IT work is if you give some people some CDs or some DVDs and say, or USB keys, and go and say, go install this operating system this way on some large number of systems, it's pretty much guaranteed that you will get differences amongst those systems. And those become very hard to trace down, as well as that sort of building being really slow. So our build environment is, we use Pixie to boot our hardware and our VMs. We use Cobbler and XCAT to install the initial image. We primarily use Cobbler. We use XCAT because our Dogwood cluster was the result of an RFP, and Lenovo came in, and part of that RFP was that XCAT was what they provided to do the builds on there. So we have both. It's not too big a deal because we really use Salt for everything except the actual initial build. We're running the open source version of Salt, and we're running 3 masters. So we run 3 masters. We run one for each cluster and one for everything else. And that's maybe a little different than some other people do. But our clusters are sufficiently different that it's been convenient to have a separate master for each one, in which case you have your separate SLS files and so on. And our other is where we have a lot of different things. So that's where our exceptions sit. So it's pretty clean for us to say, if you go on this particular master, then you're doing Longleaf, and Longleaf looks like this. You go on this one, you're doing Dogwood, and Dogwood looks like this. And those are pretty fixed. And then you say, well, you're doing something else. You go mess about in the other one, and which we call prod because we had no imagination for that one. And that means that one has got lots of little exceptions and so on, because we're dealing with that one with a lot of individual hosts. Right, so our build images are vanilla, mostly Red Hat Enterprise Linux, currently mostly 7. The only thing that's not vanilla about it is we add a Salt Minion in. And so that means when our a build comes up, it has a Salt Minion, it knows where its master is. And in the case of our 2 clusters, when a new Salt Minion comes up, it reaches out to the master and it self-registers. So that's all done. In our other environment, and this is one of the reasons why we have different masters, they don't come up and do that automatically. We manually do that. And that's just because we have so much variation in our other environment that it works out a little bit better that way. All of the host personality is laid down with Salt. Whatever the function of the host is, that is provided via Salt. Our configuration files are pushed out there. Our installation of software is pushed out that way. It's all Salt. And currently, we do this via states in top SLS. So I got, and this is as deeply technical as this talk's going to get, which is I've got some examples. So in our top SLS, and this happens to be for my Longleaf cluster, but they're much the same, We have stanzas, and the stanzas are per host type. So this is long leaf, anything that starts A to S and U to Z, asterisk. We have other ones with different naming. We have long leaf -db and so on. So they just list a bunch of states that need to be applied to that. And that has worked for us. So our base one, which is the one I highlighted, when you come in, it says what to include. And if you go down, you'll find that one of the things that we're including there is a thing called packages.base. And if we look at packages.base, it's, again, more includes where we're doing installs. And we have package.group installed, the name of development. We have to, and then we have another stanza where we have installed long leaf packages. And then we say package installed packages. And then we have a list, and there just happen to be in alphabetical order. So that's worked pretty well for us. It certainly worked pretty well in our clusters. It's has some limitations, though. It has some things which has not been perfect for us. But certainly with the I've got 3 primary Linux administrators and 2 that are kind of DevOps. And this is what has enabled us to manage 600 plus hosts, is being able to do this. Now, every single system we build has a base that is common. So everything gets NTP, everything gets the appropriate monitoring software, everything gets our Qualys vulnerability scanning, and so on. There's a base, everything gets that. And then we put packages on various places depending on what's going on. Packages and config files, of course. One of the things that goes on when you have something that works pretty well for you is that you let it work pretty well for you, and you live with issues that come up. So we've had some issues that have got a little bit more annoying in the last year or so. And roughly I describe them as race conditions, version incompatibilities, and workflow generally. And I'll tell you what our examples are and what we're going to do. So one of our race conditions is this. We install the Zabbix agent. Zabbix is our monitoring host. And when you install it out of the package, it comes with a default UID GID. One of the things that happens when you use the states like we're using them and install something like a Zabbix agent is it gets started. The trouble with that for us is that it gets started with an incorrect UID GID. And we notice this mostly because then we get spammed with a whole lot of emails from our monitoring with Zabbix complaining about inappropriate UID GID trying to contact it. Later on in the state file, a custom password and group file gets installed, and then Zabbix will continue erroring until someone manually restarts it. Because the trouble is, Zabbix doesn't know, if you're just using straight state files, it doesn't know that it's dependent on that custom password group file. So we were very fortunate that Salt State reached out to us and offered to help us go through a health check, and which was very useful. And if you get that offer, I highly recommend you take it. They're good people. And so one of the things we talked about is incorporating orchestration. So currently we don't use any of the orchestration stuff. We just set up the state of a system, the end state, and then let Salt go and do its thing. And as I say, mostly that works out. What we need to do to get rid of race conditions like this, and this is not the only one we have, is that we really need to start using requisites and declarations to eliminate these race conditions, particularly during high state. And we also can have some orchestrations that will say, don't do this yet, do this later, and so on. So that's one thing that we're going to be doing going forward. And that we haven't done yet. We're starting on some of the other stuff. The other issue that doing the way we've been doing doesn't work so well is with version issues. So when Rel 8 came along, we started getting tripped up where Rel 8 is changing the packages that they use to provide certain functionality. So IP tables, firewall D, they're changing NTPD to Crony and so on. We noticed with firewall D that this was a problem for us. And when we were going and stopping I think it was fail to ban, we would stop that and it would not restart. And it would not restart because it was all expecting IP tables and it had firewall D. And so we had to start creating target groups or start isolating our Rel 8 boxes to manage those differences better. So what we'd done in the past, and certainly Rel 6 to Rel 7, was we did a lot of testing when we were at Rel 6 to Rel 7, and we did a lot of tweaking. And in terms of tweaking, we ended up with state files that would work with both Rel 6 and Rel 7. That was a bunch of work, and it was not working trying to do the same thing Rel 7 to 8. So what we're trying to do now, and the suggestion we got from SaltStack was create target groups with grains to differentiate. Now we're already using grains for other things, and that's the example I've got here, where grains is where you can do an if statement in Salt. So here we're looking at a grains that is called FQDN, which is a fully qualified domain name, and we're seeing if certain host names are in those fully qualified domain names. If they are, we do actions, and then we have an end if, just like you have in lots of languages. It's a kind of an interesting thing with Salt and with YAML in particular, is they're not really procedural. So they're really describing an end state. And so for a lot of people who are used to writing scripts in Bash or whatever, which are very procedural, it's a little hard to get your head around doing this kind of YAML description of an end state in order to have an action happen. And so we haven't used this a lot, but we have used this, and this example I've grabbed is controlling certain mounts that happen on hosts. So we know that works. There's a bunch of grains you can grab, including the OS version and stuff like that. But we just need to structure our particular problems so that we can say, hey, if it's this version, install the right firewall software. And so we've started to go through that. And that's an easy win for us. That's a thing we're already doing. That was very useful. The other thing that we weren't doing is any workflow. So I knew Salt could do workflow. I didn't know how to do it. And as I say, we had just used the states to enforce the end goal of what we wanted. But we had a number of things that have been coming up where having a build workflow would be really useful. And that allows you a much more complex process than simply describing an end state. Sometimes you can get there with the end state, and sometimes you can't. The other thing is it's hard to separate out your build workflow from your running state if you're just using states. So we're starting to look at this, and I have to apologize to one of my admins. This is code that he's working on, so I have no and I grabbed it and said, "Do you mind if I show this?" And he was kind enough to say, "Okay." I have no idea where he's at in the build of this. But the idea here is that we should be able to, in this case, it's a certificate workflow. So when we build a certain type of host, one of the things it needs certificates for SFTP server. And at the moment, that's a highly manual process, which is also error prone. So one of the things we want to do is automate that. Now, you can't just automate that with an end state because there's processing to be done in the way that's done. One of the things we haven't been doing is using the verbs like require. So what we're working on here is a workflow that will allow us to start a build. At a point in the build, go and see if a certificate is there. If the certificate is not there, then it's going to go on and it's going to externally ask for that certificate from an API from our certificate vendor. And then it will wait and it will go back and get the certificate once it's been issued. It will apply the certificate, and then applying the certificate, of course, there's copying into certain places, renaming, and so on. And we want to do all of that as an automated workflow. And that's partway through. It certainly Salt can do this. One of my frustrations with Salt is that it's not entirely obvious how to do this. And part of that is that all your files are the same file name, if you like, they're all .sls. And so you have to look for clues inside. So you really need a level of knowledge of the syntax and the available verbs and so on before you know that you can do something. But again, we went through this with Salt and the health check, and they gave us pointers to try and go forward on that. And so we started doing that. This is the workflow piece is the most important piece of the three things that came up, because what we want to do is we want to have an automated workflow build, which we don't have right now, for any host that we're requested. And so we want to be able to do things like if someone wants a lamp stack, we want to be able to say, oh, go build a lamp stack, and have the workflow go through and build all of that. And that workflow to not be the same as my running state, because I certainly don't want to have to define live config files in my build workflow, and I don't want to risk that someone's state will overwrite someone's running config files, particularly with something like Apache files and things like that. So I want to kind of tease those two apart, have a workflow that will, in the end, kick off the cobbler build, accept the minion. The minion will come and bring and build as a host of a certain type, and that host will have in it everything that we want as a base host, and it will be fully functional at the end of it. Today, the way we build things, we don't have a fully functional host that's totally hands-off. There's a bunch of manuals. A bunch is maybe too many. There's a number of manual steps all the way through that process. So we're not doing anything mind-blowingly exciting here, I don't think. But one of the things that I think was interesting that SaltStack gave us was it gave us an opportunity to look how we're doing things. We were very much in the mode of we're really busy doing stuff and we have to get things finished. And that stops you going back and looking and saying, am I doing the right thing? Could I be doing this better? And sometimes sometimes it's better to take longer doing the piece of work you're doing and get it done and out than to take some time aside so that you can make that a more optimal process. So one of the things with the health check with SaltStack is that it made an opportunity for us to step back and look at how we're doing things and to identify where we're not doing it as well as we could, and also where we could probably get wins very straightforwardly. And that's orchestration, where we're not using that at all today, and that will do some wins for us. Making sure we use dependencies within our state files in order to, and that's kind of part of orchestration in the larger picture, so that we don't have race conditions, so we have a build flow that works very well for us. And a little bit more fine-tuned by working with things like grains better, so that we can have some decision forks in our build process. So when we do things like move to Rel 8, and there are things that are different for Rel 8, even though the majority of things are the same, we can do that with a decision by saying, hey, if this is Rel 8, go left. If this is Rel 7, go right. Like I say, we already use that a little bit, but we're not using that in the build process. We're only really using that in places where we're saying, primarily we use it for mounts, is where we use it today. So I think that's my slides. Yep. So anyone got any questions? It's not a technical deep dive, but it's been an interesting 6 months for us. We're working with SaltStack and looking through where we can do things better to fix some issues we've had.
That's awesome. Well, that, as a former academic, this is particularly dear to my heart, and I have a ton of questions for you. But before I take the stage and ask you some questions, I want to just remind people that you're welcome to ask questions if you're watching right now. You can just type it out in the chat, and Liam will be happy to answer any of those. And we've got about 20 minutes where we can do for Q&A. So I have a bunch of questions. I'm going to start basic with mine. One is, can you give an example of like a typical kind, you don't have to give specifics, but maybe a typical kind of research project that would use extensive computing resources and stuff like that?
Sure. So that's one of the weird things about running infrastructure, okay, is that we have about 1 million jobs a year get run on our clusters. And so we burn a lot of CPU. And one of the neat things that people do is they build new molecules. So what I found out is that you don't build your new molecule by going into the lab and pouring reagents and so on and so forth. You model it all first. And you model all that on big compute resources. And particularly these days, GPUs are used a lot for that. The other thing that's an interesting one is that we're getting a lot more social sciences who are coming in. Some of it is AI, and some of it is the learning intelligence stuff. So we're affiliated with a hospital and a medical school. So we do a lot of medical stuff. And there are a lot more in the last couple of years of people coming out of the medical environment with large data sets from things like the state of North Carolina's collect medical data and so on, and starting to run simulations and that across those large data sets to find out about people and illnesses, which I think is kind of cool. So
yeah, that's what I figured, is that like with this kind of computing power, I could see simulations being a pretty clear research use case for that kind of computing power. So that's awesome. So I have a couple of questions. So if I understand correctly, you have these two clusters, and is it basically that they sit they start out unallocated, essentially. Like you've got these resources available, and then when a specific purpose comes along that you need to allocate it for, that's when you allocate it and configure it as needed based on the research project, or
kind of ish and kind of not ish. So if you're at UNC at Chapel Hill, you can go to whatever the appropriate website is today internally, and you sign up for various services in the university. And one of the things you can sign up for is access to compute clusters. Once you sign up for that, and we've got a single sign-on like everyone else does, and ours is called Onion, the only name you'll ever need, just in case you're wondering, Onion. So once you have an Onion, you sign into everything with that. Once you have an Onion, you can SSH into a login node on our cluster. Once you're on the login node, you can either run software that we provide there, or you can build some software yourself if you have software you want to compile, or you can download some and put it on there and run it. And what you do is you bundle that up with a job management system, and the one we use is called Slurm. And you say, hey, Slurm, please run this job. And by the way, I need 20 CPUs and I need 10 gig of memory. And then you send that off. And sometime later, Slurm will dispatch that to a host that can provide those compute resources. So one of the neat things, and one of the things why mounts matter so much to us, is that when you sign on to that host, the login host, you want to be able to see your files. Your home directory is there and some project directories. But equally, when your job runs, it has to be able to see that on any of our 600 or 700 hosts. So once you run your job, it's there. It just writes to your home directory. They hear your results, and you can see your results. On our Dogwood cluster, which is MPI, people aren't normally asking for, 10 or 20 CPUs. They're asking for, can I have 1,500? Can I have 2,000 CPUs? That's a significant difference between the two. The line's blurring a bit, which has nothing to do with SALT, of course, but because of AMD's chipsets, we're getting a large number of CPUs available on a single box now. So some jobs that would only have had enough room to run on Dogwood, where they would span hosts, we now have enough CPUs on a single box. So, technology marches on and things change.
In some ways, it kind of strikes me as being similar to a cloud structure where you've got these resources that are available and then make them available as needed on an ad hoc basis in a certain respect. Kind of works like that. Yeah.
And there's a level of fair share scheduling. So if someone comes along and asks for lots of memory and CPU in a short period of time, their priority to get things goes down, so other people get a look in. So, and then in theory, that works out overall to give you an even access. But,
now, remind me, don't you also share resources with other universities or other projects? Like it's not just necessarily at your university.
Yeah,
don't you kind of do some cross?
We have people from other UNC universities who have access to our environment and run jobs on there, and we also have, and this is the thing we have to do with SALT, which is interesting. We had to do in the last year is we started to do what are called patron nodes. So we have this environment with a few hundred nodes, but someone says, "But I want something available all the time," and we're saying, "Well, you buy yourself a node, and it's available to you all the time." The rule with that is it has to look exactly like one of our nodes, and we'll run it for you, and we'll manage it. And so we'll manage it with SALT in exactly the same way we manage everything else. The only difference is you get a special slice in our Slurm environment that says this is reserved for you. And so we do have that from University of Greenville. They've got a patron node. They use us. And then we've also got collaborations, University of Texas, I think, and one of the universities in California where researchers are doing collaborations. But those collaborations tend to more be about moving data back and forth rather than them jumping on and running things here.
And didn't you also say that the faculty members who are using the computer resources they remote in, like do they SSH in order to use the computing resources?
Until COVID, which it just happens to be coincidental, that was the only way. You would SSH into a login node and you'd run it. There's an open source product called Open On Demand, which is a graphical interface into compute resources, and we've stood up that recently, and we're trialing that. So we're trying to get it more so that people will have the option to get a virtual environment, something that looks like a Linux desktop to them to run their stuff, rather than running batch jobs. Because there's a learning curve to running a batch job or a set of batch jobs, and that's a barrier to some people. So if we can make it so they can get a environment where they can just run MATLAB or they can run a Linux desktop and do things, even if that tops out with not much resource, they can get started. And then we figure once someone needs lots of resources, then they're incentivized to say, well, you have to take the learning curve to be able to do batch submits. So we're trying to move a little bit more into, no, you don't have to just be able to deal with bash.
I noticed on a previous slide that you had a few back that you do things with VMware, and that sounds like probably even prior to our acquisition. I'm curious, what is the VMware component in your system?
So we run a thing called, we run a VMware server farm, and it's a VMware server farm. The reason we have it is we run a thing called Secure Research Workstation, and that is where we provide isolated enclaves for people who have data that they need to work on, which they're not allowed to have exposed to the internet or anything like that. So it's a NIST 853 compliant environment, if anyone understands those numbers. And what happens is we have very controlled ingress and egress of data. And those are those secure FTP servers I talked about. The only way you get data in is through that server, which is two-factor authenticated and things. Server sits in there. They get a virtual machine, which again is two-factor authenticated. Do all their research, run their Python code, run their R code. Yeah, you know you're running something fun when someone's got two of your 32 core blades running at 100% for 3 weeks.
Yeah,
it's kind of fun.
Agreed.
Yeah. So
that's really cool.
That's my idea of success, is to have the data center people complain that we're using significantly more air conditioning resources than we were before. Yeah. So it's one of the few times when you say running CPUs at 100% is not a thing to alarm on.
Yeah.
So.
Do you keep these in like a big data center on your campus?
Yeah.
Or?
ITS runs a central data center, and it's in there. So my team, I couldn't do this if they didn't. So we don't have to rack and stack. We do most of the hardware, dealing with a vendor or doing hardware, DIMM fails or whatever like that. Partly because sysadmins like doing that stuff. And partly because it's just the way the two groups work out together.
Yeah.
So we
quick side note that data centers always seem freezing to me. I need a jacket whenever I go in them because they're trying to keep everything cool. But anyway, Simon has a question in the chat. He's wondering, after you get your current issues resolved, what's next with Salt? What are you thinking of? How you're thinking of scaling with Salt going forward?
So the next thing we want to look at with Salt is that virtual environment I just told you about, where we're running secure Windows workstations. One of the things we have to do is we have to build golden images, and those golden images get deployed. And we actually use another VMware product called Horizon View to do this, and then it gets spun up. Now, everyone who has an enclave in there wants slightly different software, and So right now it's a pretty manual process of someone getting on a golden image, booting it up, getting on the golden image, making the changes, saving it, snapshotting it, recomposing it, redeploying it, right? So one of the things we want to look at next with Salt is to say, can we use Salt to automate some of that laying down of packages in that workflow? Because we haven't really looked at Salt to say, can it help us in our Windows world? So that's a pain point that we really want to look at, and that's the thing we're going to look at. Yeah. So I'll tell you about cold and hot. And Thomas,
yeah, go for it. Thomas made a comment. Yeah.
We've got a circuit breaker that has an issue that got fixed today. Fingers crossed. And twice it's gone out and turned off all our cooling. Takes less than 15 minutes for my dogwood cluster to turn off because it's all overheating. Within 20 minutes, I've got most of my longleaf down. And if it lasts any longer than that, I start having all my storage and that go down. So yeah, there's an awful lot of heat, and there's a lot of latent heat. If your cooling goes away, but everything's still running, even if you can shut it down, it's still got latent heat. So yeah, be glad about the cold, because nothing stays up very long if you lose that cooling.
Exactly. Yeah. Right. Yeah. Yep. So you, just piggybacking on Simon's question from earlier, you mentioned a couple of slides back that there are certain things you don't do, such as like data backup or things like that. Do you have any plans in the future to maybe, if you're able to scale with automation and get it so that your team is able to do more than they're currently doing? Do you have plans to eventually offer some of those additional services if possible?
So there's a couple of things to that. And part of it's being careful about defining what backups are. So we do have one of our storage services is what we call mass storage. And currently it's, we're in the middle of transitioning, but it's a tape system, and people can put things there. We've got about 6.6 petabytes, and a researcher can put stuff there, and we will keep it for them. And we will retrieve it when they want it. And we've had people in the last year ask for stuff from 1996. I mean, they asked for stuff from a long way back. All right. And it's a bit of a pain, because when you have to transition technologies, you have to move all that data. And so we have literally billions of files, and we have lots of petabytes, and it just takes an inordinate amount of time, especially to get them off tape. So we're migrating to a new environment for that. But the closest we get to backup is we provide a service that is where your data sits in two physically different locations, and we will keep it forever, whatever forever means in the real world. But I'm careful not to call it a backup, because I can't put anything back together for you. So if I'm going to do a backup of a system for you, then what I'm going to do is I'm going to say, oh, your system died, went to pieces. I will go get all the bits and put it together, and there's your system again. And I can't do that. I don't have that. What I can do is hold data in a place and say, we're not going to touch that data, and it'll be here for you when you need it. Disaster recovery, that's a decision at the top level of the university, where they determine we're not an essential service and we can't be funded for disaster recovery. So if we die, we lose everything, then what they've said is we just start from scratch again. So that's not my decision.
So that doesn't happen, right?
You and me, yeah.
Well, you mentioned data going back to 1996. How long have you had these data clusters, or how long have you been building out these data centers and things like that?
Before I was at UNC, because I've only been there like 12 years. So we're on... I think it's the fifth generation of this type of service, where it's a central service providing for people, and that's been back. So as long as I've been there, so more than 12 years.
That's fascinating. So there might be like a lot of challenges with like keeping some of those legacy systems, as you've mentioned, and being able to maintain older systems or upgrade them. I imagine that would present a lot of challenges for your team. So
one of the reasons we have longleaf in the way it is to try and solve that problem. So with longleaf, it's the first cluster we've had that we don't have to throw it all away and get all new. So we just keep adding new boxes, and at some point we'll decide some boxes are too old and we'll take them out. But we haven't managed to find them that old yet. So 6 years is still doing viable work. And because we can have a range of CPU types and a range of CPU ages, then we can keep that going. And then we can manage that because we're using a tool like Salt, right? When we came off the precursor to this, that was just a matter of moving the applications over because we weren't changing architectures. It was Intel to Intel, so it was moving faster. The hardest thing when we did the change to longleaf was we changed from LSF, which is a IBM-owned job scheduling system, to Slurm. That was the biggest thing. Data is data is the single hardest thing to manage because the amounts are big, right? I'm now got used to them a little bit, and so I can say things like, we're moving 6 petabytes of data, and it doesn't sound huge to me. But when I think about it, it's going to take us almost 2 years to move that data off tape. I mean, that's the hardest piece, is to move data around. But the other piece that will be hard is Dogwood. Dogwood's MPI. MPI is just real fussy on its network drivers. And this is at the OS level. It's not really a thing that Salt or Ansible or anything can help us with. It's real touchy about how you build it. And so once you build it, you're kind of frozen. So we're looking at renewing our hardware maintenance on Dogwood. It's now up to 4 years old. But we're going to have to tear it all down, all the software down, and build it from scratch and build up a new version. And then that new version will be good for another 4 years, right? That's the way it works with MPI, because MPI is real finicky. When you write your code, you have to write your code so that your code knows it's talking to partners in other nodes and things, and it does that through these MPI stacks. And these MPI stacks are real fussy about the kernel and so on and so forth. So that in terms of I'm moving infrastructure, that's the hardest piece.
Very interesting. In the chat, we have somebody who's asking if he could get a download of your slides. Are you going to make your slides available anywhere?
I'll send them to you.
Okay, so if you take down Liam's email address, he can probably send them to you without a problem.
Yeah.
So.
I don't think I'm getting slides, but you can have them.
Yeah, very good. On that note, we've got just 1 minute left, so we'll just take maybe one last question if anybody has one. Probably not. So let's go ahead and close it down. I just want to say thank you so much, Liam, for your fascinating presentation. I love this stuff. I think this is really interesting to hear how academia is using SALT, of all things, to do interesting research, because research makes our world better. So this is just really awesome. So thank you so much for chatting with us about your system and letting us know about how you use SALT in your environment. So.
You're very welcome. Thank you
all right.
for coming and listening.
Yeah, thanks everybody who attended. So
bye-bye.
Bye.